Hello students, Gilly here. In this video, I'm going to wrap up the last section of the theory in the slides for week 4. And then I'm going to do a few things in R, but you'll see the things we're going to do in R are quite related to what we're doing here in this section. So obviously we're still in the context of the collective risk model. So we add that S is what we call a compound distribution. So in general, it's quite difficult to get its exact distribution. But we can use approximations. So we see two approximations here, and they're pretty simple, both of them. So I'm not going to pretend that they are necessarily always great approximations. And the first one is especially, I think we can call it simplistic. So we might say that because S is a sum of many things, by some arguments that are similar to the central limit theorem, maybe S would be approximately normal. But careful here, of course, we're summing a random number of random variables. So there's an additional source of variability. So the argument is that if n has a large mean, then you're summing a very large number of random variables, and then you might have a relatively normal distribution for this big S. Now, it's very simple approximation. A pro, you might say, well, you need very little information to use it. All you need is the expectation of S and the variance of S, because if you're fitting S to a normal, well, then you only need two parameters. You only need the mean and the variance to do your approximation. Obviously, there's a lot of limitation to this approximation, because if S is positively skewed, the right tail is probably going to be understated, because with the normal you have a completely symmetric distribution, of course. So then if your real distribution of S is skewed to the right, then the last bit, or the more extreme values on the right, are going to be understated. So but now we're going to see an example and illustrate this point. The example is this. Okay, assume a collective risk model. The frequency is Poisson, and the exponential is, the severity is exponential. This exactly fit an example we had before. Okay, so in this specific case, use a normal approximation to estimate this probability, the probability that S is bigger than this value. Now, this value might seem a bit strange. Why 24.97? You'll see in a second. It was not picked at random. So how the method works is simple. What we do is we say, okay, we know the expectation of S. Okay, because remember here we're under the assumption that we have picked a distribution for N and we have picked a distribution for X. Okay, so we do know all the moments of S. We've done some good work previously in the lecture slides to find that, okay, it's just lambda times the mean of X. In our case, the mean of X is just 2. Okay, because it's an exponential with parameter 1/2. And same thing for the variance. We know it's lambda times the second moment of X. So here it's 4 times the second moment of an exponential is 2 divided by the parameter squared. Okay, so in this specific case, we have a mean of 8 and a variance of 32. Now, the approximation simply says, okay, assume S is normal. And of course, it would be a normal with exactly the expectation we have here and the variance we have here, because those are the real expectations of S. So S, we know it's not exactly a normal, but it does have the exact average or mean 8, and the exact variance 32. So if we approximate S with the normal, we're going to, of course, use those values as the parameters mu and sigma squared. Okay, that's pretty much everything we have to do. Now we're asked to find the probability S is bigger than this value. So of course it's 1 minus the CDF evaluated at this value. So it's 1 minus the CDF of a standard normal. Here you standardize it as well. So you take 24.97 minus 8 divided by the standard deviation. Okay, now you see this number was picked because if you compute this, you're going to get 3 or I think 2.999. Okay, so then we have 1 minus CDF of 3. Okay, in R, you might use the function P norm to find this value, or you can look up at in the table of the normal values. Okay, so in essence, the problem now is actually asking you, because of this specific choice, find the probability that S is above its expectation by 3 standard deviation. Okay, because because yes, this corresponds to the mean plus 3 times the standard deviation. Now for a normal, this probability is actually quite small. It's 0.135%. Careful, if this would be in decimal, 0.00135, but here we have it in percent, so 0.135%. Now, the real probability, because S, we can find its real distribution with some work. The real probability is 1.068%. So here the point is to show you that the approximation is very poor. It's very poor because in relative terms, there's a huge difference between this and this. Okay, this we're understating the real probability by a factor of many, I mean, like 6 times or something. Okay, so my point is just that maybe you might say the absolute difference between 1% and 0.13% is only 0.8% or something, but that's not really the real comparison. The real comparison is the absolute difference, and you see that this number is many times this number, so the approximation is very poor there. Okay, now how was this value obtained? The real probability that S exceeds this value. We're going to do that at the end of the video in R. You'll see it's quite easy to find. Okay, and now just as a comment, the approximation is quite off, as we said. Why is that? I think it should make sense, and it should make sense especially because we know the skewness of S in this specific context. So in fact, if you recall an example we done before with exactly the same context, here somewhere it was another of those Josephine examples. So this problem was exactly the same thing. We had Poisson severity and we had exponential Poisson frequency and exponential severity, and we find that the skewness was this expression in terms of lambda, but for lambda equals 4, we had a skewness here, so it's substantially, I mean, I suppose it's not huge, but it's substantially different than 0. So here you have a skewed S. It kind of makes sense that the normal approximation is not especially good. Okay, now we see a second approximation, which again, there's no guarantee it's going to yield a great fit, but there's probably a much more higher likelihood than this approximation gives you a better fit, and it's the so-called translated gamma approximation. So here it's a very similar thing. We don't know the real distribution of S, but we assume that it's close to a translated gamma. Now, what's a translated gamma? Simple. It's just a gamma, a regular gamma, to which we add a constant. So if Y is a gamma here, we're going to denote the parameter alpha and beta. Okay, we call it beta to avoid confusion, okay, because lambda is already taken by the Poisson. Okay, so if Y is a regular gamma, by regular I mean it's just the good old gamma we know that takes value from 0 to infinity. But now we're going to create a new random variable that's Y plus K. So it's the translated gamma. And so you see, if K is positive, well, the support of the translated gamma is not going to be 0 to infinity. It's going to be K to infinity. But careful, K could be negative. So if K is negative, well, then the support of the translated gamma will start not at 0, but it would start at smaller values, negative values up to infinity. Okay, so what we're doing here is we're just approximating S with the distribution of this Y plus K, a translated gamma. Now, the translated gamma, why we bother having a K is it gives us more flexibility. It gives us more flexibility to fit S, because now we have 3 parameters to work with. We have the parameters alpha, beta, and K, and we pick them such that the moments of our S fit the moments of the Y, the Y plus K, the translated gamma. Okay, so it's exactly the same approach, but it's just that here we have more flexibility because we have 3 moments and we have 3 parameters to fit. Okay, and so in general, so what you do is, okay, again, we know the distribution of N and X, the frequency and the severity. So of course we can derive the expectation of S, so we can derive the variance of S, we can derive the skewness of S. Now this takes a lot more effort, and deriving the skewness of S, we've done it already in the special case of the compound Poisson. We haven't done it in the general case. Okay, but in principle you can derive the skewness of S, and then you will pick the parameters of the gamma, the translated gamma, alpha, beta, and K, such that they their moments match those things, the expectation of S. Now, you know that for a translated gamma, the mean is going to be this, because it's just the mean of y plus k. So it's obviously this. What's the variance of a translated gamma? Well, the addition of a constant here doesn't change at all the variance. Okay, so the variance of y plus k is exactly the variance of y. So it's exactly this, alpha over beta squared. And same thing, adding a constant to a random variable doesn't change at all the skewness of that random variable. So the skewness of the translated gamma is exactly the skewness of a gamma, and the skewness of a gamma is this. If you don't believe this value, look in your formula sheet and you will see it. Okay, so simple method. Now we have 3 equations and 3 unknowns. So maybe I could have solved those equations for you, but it's simple. What I mean by solving is just find alpha as a function of the skewness of S. Well, that's very easy. Then if you have alpha, you can find what's beta as a function of the variance of S, and then the skewness of S, which is a function of alpha, and so on. Okay, once you found alpha and beta, then you can find K. Okay, we're going to do that in an example in a second. So of course, an advantage here is that we have more flexibility, so we can capture the possible skewness of S because the gamma is a skewed distribution. Okay, we have more flexibility to find a decent fit. Okay, a con, well, it's a bit harder to do because we need more information. We need to know the skewness of S. Okay, which in general we don't know. We don't know the skewness of S in general. We have found it in the specific case of a compound Poisson. Okay, and also lastly, when you do the fitting, it's quite likely you're going to get a negative K. So negative K, it means that the distribution you fit, the approximation you use allows for negative values, which in reality, of course, S does not allow for negative values. So I suppose that's a drawback of the method. Okay, let's do the example. So let's do exactly the same example. Now, let's use the compound we had. The compound model we had before, but now let's just use a translated gamma to find the exact same number. And let's see if we have a better approximation. So what we do is, again, we match the moments. So we just need to solve those equations. Meaning, we need to find the alpha, the beta, and the K. So we start with the skewness because skewness is easy because in the case of, we know it already, right? And it's only function of lambda. So we already found the skewness of S in the case of Poisson frequency and exponential severity. Well, yes, we found it a bit before. Okay, it was here. Okay, and in our case, mu3 is the third moment of an exponential. Actually, we've done it here. Okay, we had this expression, and it doesn't depend on theta, the parameter of the exponential. So with this result, it's easy to find. Alpha. Okay, so alpha, the parameter of the gamma you're using for your approximation, is function of the lambda of the Poisson. Okay, that's the general expression. That's plug in our numbers. Same thing now, beta, you find it easily here as a function of the variance of S, and alpha that you now know what it is. Okay, and so you get the general expression. Theta is again the parameter of the exponential. In our case, you plugged theta was 1 off, so you get this numerical value for beta, and same thing. Now, again, once you have alpha and beta, very easy to find K. You find expectation of S minus alpha and beta. Expectation of S, of course, you know what it is. It's just lambda times the expectation of the exponential, which is 1 over theta, and et cetera, et cetera. You find this is the general expression in terms of lambda and alpha. If we plug our number, we get this. And here, as I said, you get a K that's negative. Okay, you get a K that's negative. Now let's see if this approximation is better. Using the translated gamma approximation, what we're doing is simply saying, okay, the probability S is smaller than whatever number is the probability that the translated gamma is smaller than this number, but of course it's the probability that then the regular gamma with parameters alpha and beta is smaller than X minus K. And now this we can find in R. Okay, there's no closed form expression for this, but in R the function P gamma is the CDF of a gamma. So here, for our specific problem, probability that S is bigger than that value is 1 minus the probability Y is Y is smaller than, careful here, smaller than the value, minus K, but K is negative, so it's like minus 1/8 so it's plus 8/3, and so you get, using this command in R, okay, 1 minus the CDF of a gamma at those values. Careful in R, what we call alpha is a shape parameter, 32/9, and then the rate parameter is 1/3. Okay, you get this value. Try it for yourself, you'll get this. So great, we're much closer because the real value is 106.8%, and here we're 109%. Pretty good in both in absolute terms and relative terms. So, but now this okay, it's the end of the slides, but probably you want to know more. Okay, how did we get the real value? So that's the next step. Let's do that in R. Okay, I need to share the right thing. So I have pre-prepared a little R code here that I'm going to explain. Pre-prepared because I don't trust myself to write code on the spot and don't make any mistakes. Okay, so in essence, we're gonna find the CDF of S exactly using the convolution formula we found. But we now a note, we can only do that in specific cases where the severity is something that yields a nice convolution for every choice, for every n. Okay, actually, maybe I should go back to the slides just to make sure we agree on this, or we know what we're talking about in terms of theory. So just going back to the slides for a second. Week 4 slides, obviously. What I'm going to implement is simply this formula. Okay, the CDF of S is going to be a sum. Now here, in principle, it's an infinite sum, but we're going to see that we can't really sum to infinity, so we're going to stop the sum at the high bound for which the terms that are after are pretty much 0. We're summing the CDF of the n convolution times the probability that the frequency is equal to that n. Okay, we're summing from n again to infinity, but we're gonna stop this at a certain value. Okay, recall what is f star n? It's simply the CDF of this thing. Okay, it's simply the CDF of a fixed sum of x's. But what I was saying is this: in this specific case, you know that the sum of exponentials gives you a gamma. So you know the exact distribution of Sn for every n. This is why it's easy to implement in this specific case, but it might not be if you're summing other things. Okay, if you sum log normals, to my knowledge, the sum of log normals is not something nice. Okay, so then you would not be able to implement this easily. Okay, so again, we rely on the fact that we know x1 is an exponential, and we know x1 plus x2 it's a gamma with first parameter 2 and second parameter equal to the theta, the parameter of the exponential. x1 plus x2 plus x3 is a gamma 3 theta, and so on. Okay, so that's what we're going to exploit in our code. But other than that, we're just implementing this formula. Okay, back to R. So we're going to do this in a function. Fs is going to be my CDF evaluated at x, and here we have a Poisson lambda frequency, so we're going to have one parameter which is the lambda, and we have an exponential severity with the parameter I'm going to call theta. Now let's just deal with the case that x is smaller than 0. Now, because s doesn't take negative values, the CDF evaluated at any negative value should be 0. Okay, so at the end, my function is going to return f, but I deal differently with the case that the argument is negative. So in that case, f is 0. Okay, simply because it's impossible to get negative values. So you know the probability s is smaller or equal to a negative value is always going to be 0. Now, in the case where x is 0 or exactly 0 or positive, then we implement the formula. Now, what I said is we're not going to sum to infinity because we can't, but we're going to find what I call in the code here upper n. So upper n is a very high bound such that the terms that would be after are essentially 0. Okay, they're not technically 0, but they're 0.0000 something, so they have a negligible contribution to the sum. Now here it is a bit arbitrary. I'm picking what I call upper n to be lambda, because lambda is the mean of the Poisson, plus 10 times its standard deviation. Okay, that's kind of arbitrary. If you're not satisfied with 10, you can put 100 there if you want, okay, to be more safe in a sense, but I think 10 here is plenty. 10 times the standard deviation of a Poisson, okay, because it's pretty much impossible for a Poisson to be more than 10 times higher than its mean plus the, yeah, sorry, 10, yeah, the mean plus 10 times the standard deviation is very, very far away. So the probability to be bigger than that is pretty much impossible. You know, what I mean is, you know, what's the CDF? Sorry, the CDF of a Poisson would be P Poisson. Okay, let's say a Poisson with a lambda of 1, just for illustration purpose. Okay, of course, the mean is 1. The standard deviation is 1 again if you have a lambda of 1. So what's the probability to be smaller or equal to mean plus 10 times the standard deviation is, you know, it's pretty much certain. Okay, and in fact, I think if you tried 9 here, you get still it's certain, and here, okay, 0.999. Okay, now we have our upper n, and now we implement the formula. What's the formula? Well, we deal separately with the case of n equals 0, because remember in the summation we start at n equals 0. Well, the zeroth convolution f, you know, f in the notation f star 0 is just 1. Okay, so that's the first term. Then all the other ones are just the CDFs of the of a gamma with parameter n. Okay, but now here, because R is vectorized, I can pass to the shape a vector of parameters. Here it's just going to be the shape is going to be 1, 2, 3, 4, because that's the shape for every term in the convolution formula. Okay, let me just go back to the slides for a second to make that clear. Here I'm just saying, okay, for n equals 0 here, f star 0 is 1, but then for n equals 1, it's a gamma with a shape of 1, then it's a gamma with a shape of 2, then it's a gamma with a shape of 3, and so on. But I put that in a vector in R. Okay, so here I have my vector of size upper n of the CDF of the gamma. Now, every one of these needs to be multiplied by the PMF of a Poisson. Okay, that's the Pn in the formula. Okay, so the PMF of the Poisson in R is d Poisson. Again, there's now here I can have the first case, which is the PMF at 0. Okay, because that's just the PMF of the Poisson at 0, then at 1, then at 2, then at 3, up to upper n. And now, careful with the syntax. So I should have said this is the inner part. It's the product of 2 vectors. Okay, but now in R, this is going to be the element by element product. Okay, so the first element of the first vector times the first element of the second vector, then the second element of the first vector times the second element of the second vector, and so on. If I take the sum, I get exactly what I want. Okay. Again, I don't know if I'm explaining too much, but in this formula, then the sum of f star 0 times p0, f star 1 times p1, f star 2 times p2, and so on. I sum all of those. Okay, and that's about it. That's it. Okay, now I've dealt with the case x is smaller than 0. All the other cases are dealt with this general formula. Then I return f, and I get my CDF of s. Now, just a little trick in R. Here, I'm just vectorizing this function. Okay, vectorizing the function means what? That here I declare f. Let's just see that it seems to have worked. Okay, if I take the CDF, you see at any negative number, no matter what lambda is, I should get 0. Okay, and if I take at 0, then I'm going to get a positive value, and every other number I'm going to get a positive value. Okay, it seemed to have worked, or at least it gives me something that is at least plausible. But now my point here with vectorization is if I try to pass 2 arguments here, I don't think it's going to work, right? If I pass 2 arguments, meaning I want to evaluate the CDF in like one shot, okay, one call to the function, at two x's at the same time. Okay, it doesn't work, but there's a solution to this. You vectorize the function. Okay, this is vectorize fs. You need to tell it what arguments you want vectorized. In this case, I want the x argument. I want to be able to feed to the function in one go many arguments. Okay, so if I do that, then this should work. Okay, what's the fs evaluate at 1 and at 2? Okay, those two values. Okay, nice. Okay, now I'm just gonna take a sip of something to drink because I'm thirsty. Okay, yeah. I mean, my mom would say I shouldn't drink Coke in the morning, but she's not here. So, and don't tell her. Okay, now we're pretty much done. Okay, we have found the fs. So now I can find the exact value. The exact value in our problem was evaluating fs. Evaluating fs at 2497. In our special case, okay, lambda was 4, theta was 1 off. Okay, we get this. This is not the number, hopefully, that was in the slide. Yes, 1.068%. Okay, that's the exact value. And okay, again, if you're stressed with the fact that I only use 10 here, if you put 100, I'm pretty sure you're gonna get the same thing. Okay, yes, up to all those decimals, you get the same thing. Okay, so 10 was enough. Okay, all the terms above in the summation, they don't contribute. Now, in the terms of the translated gamma, we have this is what I had on the slides as well. Okay, same number. But now one last thing. So we're pretty much done, but just as a bonus, okay, let's compare the CDFs on a graph, because now we've just compared one value. Okay, we know that at exactly this value, the approximation is pretty decent. But let's do it for pretty much all values and see on a graph what those CDFs look like. So here I have a little code to do this. So let me go over it. I'm gonna try to find the CDF. I'm gonna find the CDF on a certain range. Now here it's a bit arbitrary, but I'm gonna start it at the K, and I'm gonna stop it at this is what is this? I think this is what I want. 8 was the mean of our S, and then plus 4 times, remember the standard deviation, the variance was 32. So I'm just arbitrarily going a range that's pretty broad. Okay, 4 times more, 4 standard deviations away from the mean. Okay, and then y exact will be fs evaluated at those x values, again with the specific values for lambda and theta that we have. Y approx is our p gamma. Okay, now just careful. This is of course, p gamma is the approximation of a regular gamma. So here I'm evaluated at x, but plus the well, not plus k, minus k. Okay, but k here is minus 1/3. This is why you have a plus 8/3. Sorry. Okay, the shape is what we add. Okay, that's the shape of the approximate gamma we're using, and that's the rate of the approximate gamma we're using. Okay, now here there's a few graphical parameters. I think you know the function plot. Okay, x values, y values. Okay, we want a line. That's just the size of the line. Here I'm just picking a color. Okay, orange 2. I don't know why not orange 1, but let's go with orange 2. Okay, I'm giving names to the labels, and I'm giving title to my plot. Okay, we go here. No, it's now it's taking I think it's taking a while because it's taking a while because I picked 100 here, which is quite a lot. But anyway, I changed it to 10, but you see, I think I need to redeclare. If I do this now with 10, I think it will be much quicker. Yeah, much quicker. So anyway, I get this plot. Okay, that's the approximation, and you see, of course, there's a jump here. There's a little jump. I mean, we don't see it well, but if I pick a smaller range here, you're going to see the jump a bit better. Okay, because yes, it's 0 up to 0, but then at 0 there's a mass at 0. Okay, so careful, S is mixed here because there's a mass at 0. It's possible if n equals 0, and this has non-zero probability, then S will be 0. This is why we have a jump here. Can I make this a bit bigger maybe so we see everything? Yeah. Okay, and then let's try now. Okay, here. Sorry, I'm a bit all over the place. Let's just go back on the bigger range. Okay, and here I'm just adding a line at 1 just for illustration. And then lastly, we're going to add with the function lines, we're going to add the approximation. So the gamma approximation. So drum roll, please. Is it going to be good? Pretty good. Okay, pretty damn good. You see, it's not, okay. Now we're zoomed back. It looks like a very good approximation, except for the small values. It's not a perfect approximation because if we zoom back here, I'm going to change the range to be from 0 to 8, from minus 8/3 to 8, just to see. For smaller values, the approximation is maybe not as good. Of course, it's very bad close to 0 because the translated gamma is, of course, a continuous distribution. So it cannot capture this jump that we have. Okay, and it's giving a non zero probability to be negative, okay, which is not reality. In reality, probability to be negative is 0, and then you have a jump at 0. So this part is not approximated well. It makes sense it's not approximated well because, of course, translated gamma is a fully continuous distribution. But overall, the approximation is very solid here. And yeah, I think at the end I forgot you can add a legend here. A legend, so exact and approximate and gamma approximated, very good approximation, which I think makes sense that the approximation is good here because, you know, we're summing exponentials. Now, if we were summing a fixed number of those, we would have exactly a gamma. Now we're summing a random number of them, so it's not exactly a gamma, but still, I think it makes sense that the gamma approximation to random sum of exponentials would be quite good. Okay, but again, it's not a guarantee. The approximation will always be good. All right, I think this video is long enough as it is, so I'm going to stop here. I think I'm going to try to give you a few, at least one tutorial problem where you can practice this thing in R. Yeah, so thanks so much for listening. If you have any questions, send them my way. Bye for now.